We continue our beta-galactosidase tutorial with the particle picking part. So the first part has been relatively straightforward. So it was a relatively linear processing where we had imported micrographs, then a number of steps, but every step was taking the output of the previous step. So now we will become parallel and we can be more creative. So at the end of the last step, we had a set of micrographs, 14 micrographs in this case, with the CTF estimation for each one of these micrographs, for which we were happy with the CTF and the micrograph quality. Then now we will choose particles from these micrographs. So let us do it manually first. So for instance, we can go with the XMIP. So we choose our micrographs, these 14 micrographs, and we run first the manual step. So we see here our list of micrographs, we see here the set of particles, and the idea is that now you have to choose what is a particle and what is not a particle. So for instance, let's say that is a particle, this is a box of size 100. We can zoom in with a shift to see if this if this box is large enough or not. So probably we would like something smaller like this one, and then we would click on more particles. It is important that at this point these particles are in a closed region, so we pick all the particles nearby. Sometimes we have doubts of whether it is a particle or not. We can see that this picker is constructing a template that help us to center the particles. So this is the template that is being built, and it helps to put the particle in the middle. So the idea is that after picking a few particles, like this one, this one, this one, so after a relatively small data set, around 30 particles, we can go into the automatic mode. So this automatic mode will learn the particles that we have picked. So we can activate the training. It is asking, have you picked all particles in this area? The reason for this question is, if we have not picked here, the algorithm will understand that that is not a particle. That is a background part of the image. So it will learn the difference between background and particles. So it doesn't matter if we have missed 1-2 particles in here, it will successfully learn the data model. So yes, I have picked almost everything. So now it is training a model that extracts features from each one of the pixels of the image and then decides whether that pixel can be the center of a particle or not. And then it will find the particles in the rest of the image. So we will see now the results. So here we are the results, and as we can see, most of them are particles. So these are good particles. There have been some missing ones, so you can pick them if you want. And it has found about 500 particles in the rest of the micrographs. There are some particles here that are not good particles. So for instance, we can delete them. We may use the eraser. So we have here an eraser that if you left click with the mouse, then you are deleting particles. Then we go back to the selector, and the particle in red is the current particle. The particles have been sorted by how confident is the algorithm that that is a particle. So the algorithm is not so confident that this is a particle, so we delete it. Now the red particle is another one. We can look at it. Okay, this is not a particle. Then you this is not a particle, this is not a particle, this is not a particle, and you would continue, and the algorithm is learning from its own errors. So if we say that this is not a particle, then next time, these are particles already, so next time it will try to distinguish better between particles and non-particles. So it is learning from his errors. Now it is asking, do you want to correct the model with these errors that we have learned? Yes, we want to correct them. And then it is picking particles in the next micrograph. Again, we have about 500 particles, and we may delete this one that is not a particle. This is the less confident, less confident, less confident, and we would keep training the algorithm until we are happy. So let's say we are happy already, so let's go for the next micrograph. This is not good, this is not good, this is not good, this is not good, that's good. Then let's say in the fourth micrograph we are almost happy with the particle picking. So this is not good, this is not good, but let's say this is good enough, so we can go to an automatic step. So let's save the particles here, the coordinates that we have. So now it is creating the set of particles associated to the 2000 particles we have picked, and now we would go for the auto picking. So the auto picking, we have to choose the previous run. The previous run is this one with 2000 particles, and we may pick particles on the same set of micrographs, or as the one we have manually picked, or another one. So let's do it with the same set of micrographs. We can use multiple processors in parallel, and now it will apply the same model to the rest of micrographs. So remind that here here in the manual step we have picked only 4 micrographs, while we left 10 micrographs without picking. So now in the automatic step it is picking these 10 micrographs. If you have 5000 micrographs in your dataset, then you will pick the 4900 whatever. Good. So now it is picking. In the meantime, XMIP is not the only algorithm that picks particles. It is pretty good. It has a relatively low number of false positives, false negatives, but still we can try some other algorithms. For instance, we can try Iman Boxer. So we can try Iman Boxer. So we would choose the same set of micrographs, these 14 micrographs with good CTFs. Then we execute Iman on them. So this is also an interactive tool to choose particles. So now it is opening these micrographs, and we have here several windows. So one of the windows is the current micrograph. This is the list of micrographs, and this is the list of particles. And there should be another window, this one here, that has the parameters for the algorithm. So a good algorithm for picking particles is this swarm. So this swarm will try to find particles similar to the thing that you have picked. So let's say I say this is a particle. So the algorithm suggests that all these other should also be particles. For instance, this is not. And then it corrects with this information. This is not. Let's say that this is. We can center it again. And then we can center this one. We can give this one. We can center it. It is important that you give accurate information. If you don't correct, then the algorithm quickly derives into very bad predictions, because the model drifts from good data to bad data. Okay, so we are happy with this picking. So this was the first micrograph, and we can move to the next. And then we move to the next. We see that there are some errors like this one, but still most of the things picked are correct. And then we would go for all of them. So we would go for all micrographs here. And something bad with this swarm is that you have to click particle by micrograph by micrograph. It cannot be launched in automatic. So if you have a large number of micrographs, this is not easy to apply. Okay, so we would go for all of them. We have already done that. So you would save the protocol output once you have gone over all micrographs. And here the automatic picking already finished, so it has found 7,000 particles in all micrographs. And for instance, this one of Iman, we can see it has generated 2,000 particles in 4 micrographs that we have covered. So I already did that in this blue part here, so I will delete these steps that we have just done, and we will explore the results from the previously picked particles. So in Iman we found 7,000 particles. In XMIP we found 10,000 particles. Sparks, this is another one. This is fully automatic, so you don't have to click on any one of the micrographs. You don't have to choose any particle. So you only need to give what is the particle size of the object that you are looking for, some parameters. With this wizard you can choose the parameters so that you are sure that it is predicting the right thing. And then this one predicted 11,000 particles. So the question is, which one is right? So for every algorithm has its own false positives, false negatives. So can we make something better? So here in Scipion you have this consensus picking. You have it there. So the consensus picking, you can choose several pickers. So let's say I choose Iman, XMIP, and Sparks. You say that two coordinates are pointing to the same particle if they differ in less than 10 pixels. And here it is where you can be very creative also. So you believe a particle is a particle if at least one algorithm has chosen it, or you believe that a particle is a particle if you see that 2 or more algorithms have chosen it, or 3 algorithms or 4 algorithms. So here you choose the algorithms, you choose them through this magnifier. So with the magnifier you choose which are the pickers that you want to use, and then you say, I believe a particle, in this example, I believe a particle is a particle if at least 2 of them have found it. And the consensus picking is about 7,000 particles, and we can verify with the analyzed results whether these picked particles make sense or not. So here we have which are the particles selected by at least 2 algorithms, and they look good. They are reasonably good. For instance, this one is on the carbon edge, so we hope you can delete it now. So with shift, and then you would generate a new set of coordinates, but if you have many micrographs this is not very convenient. So I will not save these coordinates, and then you would expect that there is some algorithm behind that is able to remove these bad particles, and these algorithms will come later. So once you have your coordinates, the output of a picking is a set of coordinates. So now we extract them. So for extracting particles, you choose the set of coordinates that you want to extract. then you have to give what is the CTF estimation that you want to attach to these extracted particles. You may pick the particles from the same set of micrographs as you have picked, or for instance you can have several versions of the set of micrographs with different downsampling factors, and then you may choose from any of these sets. And also you may choose, for instance, remind that we inverted the contrast at this point, so we may choose the particles from the non-inverted micrographs and so on. So all this is done through this micrograph source. Then while extracting, you can change the downsampling factor, and depending, you may downsample by 1, that is no downsampling, downsample by 2, that means the images have to be twice smaller, downsampling by 3 times smaller the images, and then this wizard will suggest what is the box size for the particles based on the box size that you chose while picking particles. Then you can choose what to do with the pixels outside. So if the particle is very much on the border of the micrograph and the box goes out of the micrograph, how to fill the particles, the pixels in there. You can also remove dust. So sometimes micrographs have hotspots, or they have small scratches or things that they clearly are not following the statistics of the image. So everything above or below 3 standard deviations of the mean, they are set to some they are saturated, and actually it is this 3 is configurable, so you can, in this case it is 5, this is the default value. And then you may decide whether to invert the contrast with respect to the micrographs you have picked. So remind, many algorithms expect for white particles over black background. This is not the case of FreeAlign. FreeAlign expects black particles. And then you may phase flip. So the phase flip, the CTF is an oscillating function in Fourier space. So that means that for some frequencies, the particles are projected like white over black, while some other frequencies are projected like black over white. So this phase flipping is making everything consistent, and everything will be projected like white over black. It is not correcting for the envelope, so the envelope, you still have a damping that will be corrected later while doing the 3D reconstruction. And then we normally normalize the images, so the gray values in each one of the micrographs may differ, and this normalization is assuming that the eyes in all micrographs have the same has the same statistics. In particular, they have 0 mean and standard deviation 1. So once you have extracted the particles, you can sort them by what we call them the statistics, how strange this particle is in this dataset. So we have already done that, and when you see the particles that are extracted, you see the particles as a gallery. So each one of these particles is coming from a different micrograph, so you may see them as a gallery, as in here, or you may see them as a table. So this table, for instance, these are the different particles, and you have different pieces of information attached to them. So for instance, what is the defocus, and this set score that has been computed by the statistics that we just mentioned. So particles are sorted by set score, and you see that the set score is something that goes from 0 to a positive number. It is unbounded, so in this case it goes at as high as 12. So bad particles or strange particles go normally to the end. So we may go back to the gallery view. So we see that the end of the list, we are at the end of this gallery, go normally all these bad things picked by at least 2 algorithms. So now we may reject the bad things either visually, so you may say this particle, this, you disable, and you would continue with all of them. But this is again not so convenient if you have thousands of particles. And another possibility is that you go to the table view, you choose a threshold. For instance, let's say 3. 3 is a magical number, because if things were Gaussian between -3 and 3, you would have 99% of the distribution of your population. So you may take a magical number or any threshold that you like and say select from here, disable, and then produce a set of particles. In this case, we have rejected about 300 particles from almost 7,000 to 6,600. So 400 particles have been rejected. We will not do that now because we already did. And then we would have a subset of particles. These are the ones that we rejected in this case, and this you may name them with a label that helps you to remember what they are. So in this case, they are the ones with a low set score. So this would be the tutorial for particle picking. Here you can be very creative. You see that we have many algorithms in Scipion available, so you can use the one of your choice, and then you may play with the consensus. You may play with how particles are extracted, at which downsampling, which CTF you want to attach to them, how you reject particles. This rejection can also be done automatically, so if you set the threshold in the form, you don't have to reject them manually. And in the next tutorial, we will go to the 2D pruning of these particles and understanding what we have picked.